Dear students, in this example we can see that it says that there are two monochromatic rays of light that are incident normally on the face AB of an isosceles right-angled prism ABC. The refractive indices of the glass prism for the two rays are different, which are 1.38 and 1.52. Then it is asking us trace the path of these rays after entering through the prism. So it has already been marked that this angle is 45 and 45 because it's an isosceles right angled prism. So this is very simple for us that we know because it is a normal incidence. So the refraction will happen in such a way that it just goes without any deflection because of the Snell's law. Because if I is 0, then R should also be 0. That incidence angle is 0, so refractive angle will also be 0. But now there's something really interesting in this case, that now this is a denser medium and this is a rarer medium. Now the light ray is moving from a rarer to a denser medium, so it will be a bit tricky for us to know that if total internal reflection is happening or refraction is happening at these two points. So what we do is we first draw the normal, and when we draw the normal, things start to get even clearer. Like I have drawn the normal for both the rays, and I figure out that this angle of incidence for this refraction or TIR, that is total internal reflection, we don't know what is going to happen, it is 45. So incidence is for both the cases is 45 degrees. So now because we know the incidence is 45 degrees, let's see if this incidence angle 45 degrees is greater than the critical angle or not. First of all, let's find the critical angle. What will it be? So let's find the critical angle for both the refractive indexes, because here the mu1 is 1.38 and here the refractive index is 1.52. So for these two refractive indices, we'll find the critical angle. So let's find the critical angle. So critical angle for the first refraction, we can write sine C1 should be equal to 1 by mu1, 1 upon 1.38, because mu1 is 3.38. For the other refraction, sine C2 will be equal to 1 upon 1.52. Now we already know why sine C is equals to 1 by mu. For the same reason that we use the Snell's law at the place where total internal reflection is happening for the critical angle case, where the light ray goes at an angle of 90 degrees. So we just do sine critical mu sine C is equals to 1 for air. So this is how we get it as sine C is equals to 1 by mu. So we know both the critical angles. So let's see what is sine incidence, because sine of incidence for both of them is same. So sine of incidence, that is sine 45 degrees, is equals to 1 by root 2 for 45 degrees. So root 2 we can write it as 1.414. So now the very interesting thing is that this is the incidence angle. So let's see that for the first case, is the incidence greater than critical angle or lesser than critical angle? So we find out that this sine angle is greater. For example, here the incidence angle is lesser than critical angle for the same reason, because sine I is less than sine C1. This is sine I and this is less than sine C1, because this is 1 upon 1.414 and this is 1 upon 1.38. For the same reason, we see that in this case something very interesting is happening, that here our incidence is greater than the second critical angle. So that means for the second ray, now we are damn sure that it will be a case of total internal reflection. That means there will be no refraction, it will just suffer a reflection. So the reflection will look something like this, because angle of incidence is equals to angle of reflection for this case. So this will also be 45. So we have done it for the second ray. We know that the second ray will go like this. It will totally reflect. Whereas for the first one, reflection will only happen because the incidence angle is lesser than the critical angle. So because we are going from a denser medium to a rarer medium, so what happens is it bends away from the normal. So this angle of refraction is greater than 45 for sure. So we can say that this angle of refraction is R1. So now calculating R1 can be a very simple thing using the Snell's law. So we'll do that in the next page. So to calculate R1, what we do is we apply the Snell's law, which states that 1.38 into sine of 45 degrees. So Snell's law states that mu into sine theta is constant, should be equal to, this is refractive index of air, to sine of R1. So from here we can easily say that R1 is equals to sine inverse of 1.38 upon root 2. So we have calculated R1. So this is how we are going to answer our question as precise as possible. We have even given this angle on the next page. That will be nothing but sine inverse of 1.38 upon root 2. So this is the answer to this question from optics.